Hello and greetings from IIT Kanpur. So, in the previous discussion, we saw that as IC technology evolves, there is an attempt to make the devices smaller and smaller. So, as a result, the chips become smaller, and we saw the reasons why that is being done. So, in this lecture, we will again take a closer look at that, and I'm sure almost all of you might have heard about what the Moore's law, which is very popular, and we'll see what this Moore's law is all about, and it's more about formalization of the way the roadmaps for VLSI technology came about. The disclaimer. So let's go to the outline. So today I would be trying to highlight how Gordon Moore identified the underlying economic drive for scaling, and essentially the device density, as it increases, there is a trade-off in terms of cost as well as yield. Okay. So now with technology improvement, the optimum cost drops over the years. So somehow Gordon Moore managed to observe this, and what came to be known as the Moore's law. Strictly not a law, that's why I put it within quotes, but it seems to be working as though it's a law. Okay, as though something, that's the way things should progress. So the Moore's law is observed not in various categories of ICs, and typically the category of ICs that people follow in order to illustrate Moore's law, for example, is the central processing unit chips, CPU chips, which are doing a lot of logic based chips. And what is very fascinating is this law, or this trend, if I may say so, has continued for more than almost 6 decades. And not just that, of course it keeps evolving, and sometimes in a few cases, some of the technologies it has been faster than Moore's law, sometimes slower, but it gives a general idea. In last 6 decades it has held its ground. And it's not just the CPU, a lot of support technologies that also need to keep up, and they have kept up. So it's a technological marvel that this has happened, but the guidance was given by the Moore's law. So it all started with this prescient paper by Gordon Moore. At that time, he was working Fairchild Semiconductors. He was the director of research and R&D in that company. And as you might remember from our earlier lecture, Robert Noyce actually came up with the the concept of integrated circuits, putting more than one device and forming a complete circuit on the chip at Fairchild. So they had started developing more and more sophisticated chips, and there were discussions, there were general ideas what was happening, and actually the electronics journal asked him to write an article, and what they call the expert looks ahead, and this is where the so-called Moore's law finds its birth. The title of the paper is Cramming More Components onto Integrated Circuits. And I would strongly encourage all of you, if you can, try and download this paper and read it. Why I say that is, it's amazing to see the clarity of ideas and vision that is presented in that, both what is happening at that time and also being able to be in a position to look ahead. In fact, some of the things that he says, mind you, this was published in 1965, right? So at that time, he was able to envision some of the things that would become commonplace. So that I thought was very fascinating, that how computers can be made portable and so on. So those things I found it to be very fascinating, and also the clarity of thought. I think it's worthwhile for any student of technology. Now, what was done in this paper? What was presented in this paper? Essentially, the interplay of economics and technology, essentially to optimize cost, of course, how to get the lowest cost, that is the whole thing. So economics pushes industry to scale to reduce transistor cost. We saw that even in the previous discussion, right? If you pack in many more devices on a small die, of course, you will be able to get lower cost, because all the fixed cost gets divided and only the variable cost that is associated with each die, that is packaging and testing and all those things, those will remain, but the manufacturing cost comes down. So that's no brainer, right? So that you have to go for smaller and smaller devices if that's the case. But how much small should you make so that you don't end up losing money in trying to overachieve? So that's where it was noticed that for a given technology, at a given point of time, there is a maximum amount of device you can pack in a chip. If you try to pack more than that, you end up hurting the yield of the dies on that particular wafer. So this interplay was spotted very nicely by Gordon Moore, and he shared it with the world in that paper in 1965. Okay, he discerned that scaling trend, and what he shared ended up becoming, in some ways, a self-fulfilling truth, you can say, because once you notice it and you are able to tell something reasonable, people tried doing it, it happened, and it kept happening. So this interaction that he spotted was the mainstay for defining the roadmap for IC industries for the next several decades. In fact, in 1965, what he did, he tried to predict what will happen in 1975. In 1975, he did some revisions, and the law, so-called law, continued after that. So what is the summary of finding? Let's go into the details now. So this is the plot that he made. This is the actual plot that he drew that I got from the Intel website, and version of this, of course, a printed version of this with proper fonts and not rather than the cursive handwriting that you see here, is available in that paper. So he plotted on the x-axis number of components per integrated circuit, per IC, number of components that are present in it, IC of a given size, and the relative manufacturing cost per component. Obviously, as you keep increasing the number of components in the IC, per component cost will come down, because in the same chip you are getting it and the cost will come down. And that's what we see in the early parts of these curves. It's coming down as you keep increasing the number of components in the chip. But if you keep on increasing the number of devices in a chip, what will happen is at some point your yield will suffer. The reason is you may not be able to define the devices properly. The interconnects has to come properly, so there can be some shorting, and sometimes there can be open because what is supposed to be etched ends up etching what should not be etched. So you find that it becomes tricky, and even the design and everything becomes complicated as you cram more and more devices within the same chip. So what ends up happening is you find a reverse trend. As you go beyond a certain density for a given technology, you find that the cost actually starts going up, because you're fabricating all that with a lot of care, but your number of actual devices which are useful that is coming out is very less. So there's no point beyond a point. So that is the part that it starts going up. So clearly there is a sweet spot for a given technology. So what was available in 1962, based on that, they must have done a lot of experiments in their labs. They would have done various types of devices, and from the data he has plotted 1962 and what he saw in 1965. These are estimates of what is happening, he tried to tell in 1970. So what you find is, if the yield and the ability to control the size of the device and make small devices improves, you are able to pack more devices, so the cost comes down overall. And also you are sure that you will get what you are wanting. So this optimum for a given technology keeps decreasing, as you notice, with over the years. Why is this happening? Because the technology is becoming more and more sophisticated. Now this can be a target. Make sure that instead of trying to do anything which is small, have a clear target. How much should be the size that you should target for maybe the next 3 years or next 2 years. So this way there can be a roadmap or a look ahead, and that helps the fabs and the labs that are associated with fabrication and device processing can work on various parts of the fabrication process. So the ability to handle complex and scale device, as it improves in technology, the cost minima decreases. That means the number of components with each successive technology you can promise to deliver more to the customer. So that is the best part of this process. So this trend in component per circuit with technology, he had estimated for 1970, 1975, 1970, and also he predicted apparently for future years. If you read that, he's trying to predict this is how the trend would be. So now, based on this, what was his conclusion? So this is a trend. So this is understood. So now we have to convert it into some numbers. So he goes ahead and plots the number of components as a function in the log scale on the y-axis, x-axis in the years. Of course, the year in a way represents the technology, the best of the technology that's available in that company. Now, what he found was, in the log scale, this is falling in a straight line. That is, it is exponentially increasing the number of devices that you can make. So he had only 4 points, right? In 62, some 63 from Fairchild, and also 65, and also some very early results, 1959, when around just after the invention of the ICs. So then he does an extrapolation. Extrapolation is always tricky because a slight variation you'll extrapolate in some other direction, and that uncertainty is of course expected. It's a part of science, part of reality. So he extrapolates for the future years. And what does he conclude? And this is where his prescientness or the ability to look into the future is remarkable. Number of components in the IC, he says, will double every year based on whatever he got here. Note that this is log scale, log to the base 2. Okay, so now he doubles every year. Now he found that that trend does continue, but around 1975 he realizes that maybe it cannot be so fast. Initial days, since a lot of unknowns were getting solved very quickly and it was low hanging fruit, so to say, he was able to find the trajectory of how it will scale. But after birds, he found that it's not so easy, so he revised it a little. So and also how the various industries were working, and I'm sure they must have he must have seen what's happening in the various conferences, etc. So in 1975, he slightly tweaks his law, so to say, that it will double every 2 years. And this observed trend is what is known as Moore's law. That is, number of components in an IC for a given technology. Here we are talking of logic microprocessor technology, for example. It will keep doubling every 2 years. For the most part, this has been kept. That is what we have seen over the decades. With slight modification, when there are roadblocks, then maybe it may slow down. Suddenly there will be a breakthrough, remarkable breakthrough, so you'll have slightly higher thing. So it depends on that. So, but this has kept steady. So the general trend has sustained for nearly 60 years, and not just that, it tries to tell what we should target for the coming years. So how is it useful? So let us see. So this is the trend that we see. This is post facto, right? Over the years 1970 all the way to 2021, 22 or something. So this I took it from Moore's Law is Alive and Well, an article by Mike Anderson, and in medium.com. So he has done that. So you can see what a remarkable thing that has happened over the years. The number of transistors that get packed into the single chip keeps going up exponentially over the years. So for example, this is shown for Intel and non-Intel CPUs, type devices, microprocessor type chips. So the first 4004 Intel's 4004 microprocessor had 2200 transistors, if I'm not wrong, around of the order of 1000. So that is around 1971 or so. Okay, and soon it crosses a million in the 90s, billion in the first decade of this century, and then it is on its way towards a trillion. And I would want all the students who are listening to this to please note these numbers. And as engineers or people of science, it's important that we give respect to these numbers. When you say 1,000 and then you say a million, one should get a feel for what's the range of jump that we are getting. If you want to count 1,000, counting 1, 2, 3 like that, one number every second, it will almost take 16 minutes, 16.6 or 16.7 minutes. Okay. But on the other hand, if you want to count million, 1, 2, 3, 4 like that continuously, so that many seconds will be there, and that ends up being 11.6 days. Imagine that. You could do this within 1 hour, counting up to 1,000, but if you had to count up to million, you need more than 10 days. Okay, 11.6 days, you can do the calculation. Okay. Now, if it were a billion, what would you need? You need 31.7, if I'm not wrong, check the numbers, years. So, million you can count in days, 1 per second, but if you are talking of billion, it will be 3 decades. Okay. Trillion, obviously it is 1,000 more. It ends up becoming 317 centuries, if you want to count. So that means that many transistors are being packed in that small area. So you can imagine what type of sophistication and what type of statistical control, all that is needed to ensure that all these devices are working. And that's a remarkable thing that we have in semiconductor VLSI processing. And interestingly, we continue to improve by using the tools that we build to make it better and better. So you can see over the years it is roughly kept there, but it's sort of coming down below here, slightly coming down, but some of them are going up. That's because of the technology that they are using. So, and somehow the best technology will end up getting the market share, and as a result they'll get funding. So and that technology slowly gets adopted. So there is a constant competition which ensures that this happens. So now Moore's law, the way he observed it, what is interesting is this trend has kindled the imagination of a lot of people, and over time, instead of talking of number of devices packed in a particular chip, people want to see calculations per second for the amount of dollars that you spend in getting the calculation. So there is a very interesting paper here. Ray Kurzweil has originally written this paper. It was updated by Steve Urofsson, I think. I hope I'm pronouncing it correct. In the slides you can read it. This is Future Ventures. They have tried to look at it not in terms of just electronics, but for computation all the way. So mechanical devices that were used for computing. Then you had vacuum tubes, relays in electrical systems, then vacuum tubes birthed from electronics, and then discrete transistors, and then we come into the age of integrated circuits, and you can see the trend is mapped very nicely. So this is another form of the Moore's law, so to say. And what is interesting is Intel was the one that was leading all the way up to this point, and then now we have NVIDIA chips which have more computation for the same cost. So and they are using slightly different approaches, and with neuromorphic computing and other things coming up, I think there is a big jump in the way things are being done. Of course, a lot of memory is needed in this. So, but then this will set the benchmark that this is what we want to achieve in the next 2 years. So the companies will put in money to see what is needed, what are the technologies needed, and they'll move towards that. It is not just logic devices. We find that the same thing is also true with memories. This is a slightly dated slide. I took this from Professor Abai's book, just to give an idea that even the DRAMs have kept pace. It keeps going up, right? And this is log scale, remember that. In fact, these things can become, the densities can go faster, Part of the reason is memories are usually very much arranged. They are in arrays. So as a result, fabrication usually is much easier. Okay, and easier in its own way, but of course the demand is more. You end up packing a lot more. So you are always at the boundary of what you can do and you cannot do, and the person who manages to do it wins the market. So that's how it works. So DRAM technology has progressed very rapidly. It continues to progress. In fact, today some newer technologies are coming up. AI application has increased memory requirements significantly. As all of us know, that it searches around the world and does all sorts of neuromorphic computing and so on. All those approaches are being invoked. So you need 3D NAND stacked memory cells is one of the latest technologies, and these have mind-blowingly high number of transistors. So some of the chips can have of the order of 1 trillion, because it goes 3D, 3 dimensions, not just planar. It's stacked on top of each other. So you have greater than 1 trillion transistors per chip, and all could be achieved in some very specialized devices. So it's not just in silicon. In other support technology, for example, all of us will remember our magnetic hard drives. This too is slightly dated, but this captures what I'm trying to tell, what happened over the decades. You can see that this is faster than Moore's law's prediction in terms of how it progressed. And the technology that you have, these hard drives with magnetic disks spinning and it's being sensed, is mind-blowing, and it's no less amazing compared to what the VLSI silicon-based technology does. And this is the reason why VLSI technology has developed. It's not just a singular approach. There are all sorts of technologies that have been supportive of it. They too have kept pace or even done better in some instances, if you look at it purely from the science and technology point of view. So that being said, what one can say is the Moore's law trudges along. And this is something that somebody who has had a chance to look at this for almost 2.5 to 3 decades, I'm amazed by the human ingenuity. Every time they say that the next generation is going to be such and such, the dimensions of the device is going to be so much, you find that people are not just doing that, they are ensuring that they are able to make products. It's not about making one device or one chip. You have to make lots of chips and you should be able to sell them. And the proof, of course, is there in the power of electronics that we are all handling, or we are all seeing, we are witness to. So there are lots of naysayers. Almost everybody comes and says that, I remember more than a decade ago, there is a red brick wall. Why tunneling current is going to come and so on. Then the power question came. So, but people work around. If it cannot be done, processing is of course one of the front runners. If you can do it at that level, good. Otherwise, with clever circuit designs, clever architectures of digital circuits, you can and system level design. So you can make sure that the performance, and that's what is the criteria now, not just the cost. So and this was highlighted also in one of the previous lectures, that performance is what we need to optimize. So let me give the takeaways for this particular discussion we had. Just to recap in a way, the cost drops with increasing device packing density. This is obvious. I think this is secondary school arithmetic, I would say. But as the packing density increases, yield drops, and that will lead to cost increase. So this is the key thing that one has to note, and how it does, that understanding is important, and that anybody who wants to set up a fab needs to have those analysis and make sure that they are working at the right cost point. So the optimum cost actually decreases as technology advances, because you are able to ensure that the yield is not compromised. And also the cost of making the device comes down because you are ensuring that a lot more devices are being made. The memory technology has supported, and it also follows memory technology, and various other chips also, categories of chips also have seen similar progress as the microprocessor industry. Because the good technology, once it is available, of course it can be shared across for all sorts of applications. The key point I want you to remember is Moore's law, at least as of today, and I can see at least for the next few years, there is enough confidence in the industry that the Moore's law, at least in terms of the computation and so on, will continue. Sometimes we talk of equivalence to what the original canonical form of making a device is there, but as far as performance is concerned, they are able to deliver for the same cost. So that is what is the new form of the Moore's law. Okay. So now next we will look into some methods of scaling in the next lecture.